Thank you for the nice introduction. I do appreciate the company for putting this workshop together, and also for the invitation to give me the opportunity to give a presentation and discuss with my colleagues. We all know if we have a happy gut, we have a health gut, as a human, we all feel happy. But for the animals, if they have a healthy gut, so that means they will have a good performance and growth. So what's the definition of the health gut? So in general, it should be kept in homeostasis while maximize its function. So there are around 4 aspects to describe healthy gut. The first would be the optimal digestive and absorptive functions. And the second would be effective barrier function. The third one is effective but low-cost immune system. The last one would be small and diverse and stable microbiota. So in my talk, I will touch the last 3 points. So from this slide, on the red line is based list the functions of a builder, what he can do. The first one, as the first speaker described, is the major energy source for colon enterocytes. And in addition to its function as nutrient, it also acts as messengers, which regulate a variety of cellular functions, which include anti-inflammatory effect and the protection of the epithelium barrier. In addition, it regulates the gut tissue proliferation and the development. So I have listed the major mechanisms, the molecular mechanisms of a butyric effect in this slide. It mainly includes the butyrin can inhibit the histone deacetylase. That means it can increase transcription levels. Secondly, it can interact with the cell surface receptors, as Philip just mentioned. So therefore, to influence the cell signaling. And third one, it would regulate cell proliferation and apoptosis factors. In addition, it enhances the intestinal alkaline phosphatase, and I will touch upon in my following slides. And it also induces gut-inducible heat shock proteins, which also regulate a variety of cellular activities. It can down-regulate bacteria virus signals. Finally, it moderates gut microbiota composition and in turn to affect bacterial metabolites. So it has a lot of cellular functions which benefits the gut health. So what's the source of butyrate? It can be produced by colon fermentation by gut bacteria, as Philip just pointed out. I showed you some slides. And also, we can also supply the butyrate in the feed to make the works. And this slide basically shows how colon fermentation. When the gut has a dietary fiber, so as the fermentation results, it will change the bacterial composition and reduce the pH value in the gut. It can also enhance the short-chain fatty acid production. The short-chain fatty acid production mainly includes the acetate, butyrate, and the bromic acid plus the gas. And this is our early publication in early 2000. As I joined the AFC, that's our first paper. And actually, it's also first publication using 16S RNA sequence to explore, to investigate the microbial community structure and constructions in boilers, but it's mucosa-associated bacterial population. So as you can tell, so the butyrate-producing bacteria, this one is predominant, and also Faecalibacteria processinii, which is also a butyrate-producing bacteria. At that time, because this almost back to almost 20 years ago, the 16S database is quite small, and the tools we have, we don't have the Illumina like sequence tools. So that time, what we can only do, we can generate a gene library. So you can tell the total clone number is 126 clones, but it's just the tip of the iceberg. Even though the number is small, but it is indicate the trends that butyrate-producing bacteria is very important. So nowadays, the 16S RNA database become very big. So, and there used to be those groups, they always identified unculturable bacteria, now become clear. So majority of the butyrate-producing bacteria belongs to Clostridium cluster 14, and also 4, and including other Clostridium bacteria, Clostridia bacteria. And the one particular, as indicated in last slide, it's Faecalibacteria processinii, which is the one of the major butyrate-producing bacteria. It's also mucosa colonizer. So I'm going to let's look at what is the effective berry functions. So this diagram shows the berry structure. So it's composed of M cells and enterocytes, Galap cells, and also some immune cells. And the T junction, tight junction, as indicated by the bars, plays a critical role in the gut integrity. So when the junction is damaged, the guts become leaking, then it's going to be a problem. And your cause the inflammation affect the animal growth performance. So when we have a leaking gut, so in general, the inflammation will increase, the immune response will increase, and the nutrition efficiency will decrease. As a result, this will affect adversely animal performance. So the question is, how can we prevent the gut leaking? Is it possible to repair the gut damages? The next two slides, I'm going to show, give an example whether the butyrate can repair the gut damage. So this work was done by Jack Ho in China. Their groups, they're working on piglets. Basically, the idea, they artificially induced the gut damage by infusing acetic acid. And then, meanwhile, they treat with the butyrate, which is a type of the butyrate, and to see if the butyrate can repair the gut damage. So as you can see from this slide, this is control group. This is the acidic challenging the piglets. This is the butyrate treated the groups. So for villi heads and the crepe and the depths, and also you look at the gapillary cells, and also intraepithelial lymphocyte cells, and also lymphocyte density. So you can see in acidic challenging the piglets, those parameters are either up or down significantly. So when the pigs were treated with the butyrate, so all the parameters almost back to the control groups. So that means the application, administration of the butyrate can reverse the gut damage to elevate the gut injury. And this is another these are also a piece of the results of the immunoblots. Basically, they check the proteins, those key proteins for apoptosis and also for T-junction formation. The top one is caspase 3, which is the key enzyme for apoptosis. The bottom one is clostridine 1, which is a key factor for T-junction formation. So as you can tell, the acidic treatment basically increase the production of the caspase 3 and down-regulated the clostridine 1 with the treatment of a butyrin. So both proteins were back to close to the control piglets, which have no treatment. So, and also they check the EGF receptor level in acidic treated piglets. The receptor level was down-regulated significantly, but in the control groups and butyrin treated groups, there's no significant difference. Therefore, the conclusion is that the butyrin, the treatment can inhibit the apoptosis, promote tight junction formation, and activate EGF receptor signaling. Therefore, to elevate the intestinal injury. So let's look at the effective and the low-cost immune system. So ideally, we hope in the situation there's no adaptive, but only immune response, only innate immune response, and also no or less gut inflammation. And as such, the energies used for immune response can be used for animal growth. I think the first speaker has clearly indicated this in his speech. So what for the gut inflammation, because we know the subtle gut inflammation is always there. And the gut inflammation mostly results from epithelial damage. And the bacteria and the toxin and their toxins, for example, LPS, are one of the common factors to cause the gut inflammation. So can we reduce the inflammation? And I think if we can increase the gut integrity, that would be one option. And also if we can increase the innate immune response, this would include removal of the inflammation-inducing components such as LPS, and also reduce the production of the pro-inflammatory cytokines and the increase of anti-inflammatory molecules. Additionally, increase of the production of an antimicrobial peptide would be another choice. And finally, and also the other a major point would be increase the intestinal alkaline phosphatase. That we call simplified IAP. IAP is the marker for gut development and maturity. In addition, it is also the anti-inflammation enzymes. So it has several functions, but those specifically associated with inflammation, including detoxification of bacterial endotoxins such as LPS, and also regulation in intestinal bacterial translocation. The translocation will cause sepsis, and the LPS will cause local or even some systematic inflammation, as I mentioned at the beginning. The way IAP works, and for those bound in the lumen, also bound on membrane, the many dephosphorate LPS and detoxify its activity, and therefore to block the binding to toll-like receptor 4, and the result no or less LPS induced intracellular signaling, therefore reduce the inflammation. And for those located inside of the cells, it can block the NF-kP translocation to the nucleus, and therefore down-regulate the pro-inflammatory response, such as interleukin-8 and TNF-alpha. And this is one example. I think it's it's in vitro studies. The author used human cancer cells, and they test different lengths of the short-chain fatty acids, including C2, C3, C4, up to C6. C4 is build rate. This is an broad analysis. So as you can tell, on the top, the IAP, the C4 build rate enhance the protection of the IAP. So that means it probably will increase the activity of the IAP for detoxification of LPS, which help to reduce the gut inflammation. And lastly, I'm going to touch upon the microbiota. As we said, ideally, we wish to have small, diverse, and stable microbiota. So we always struggle with how can we balance for sufficient the microbiota, which allow for sufficient immune and gut tissue development. The other one would be for the colonization resistance to endemic infections by pathogens. And also, we also hope it will have a good nutrient efficiency, including digestion and fermentation. Overloaded gut microbiota will compete with animals for nutrients that can be used for animal growth. So the questions, do we have any tools to do it? Can build rate help it? So next few slides, I will cite the work from the immersive groups, and he just gave a talk. So they have done some excellent jobs. So in the first slide, basically, they look at the effect of the build rate on the salmonella burden and the shedding. And as you can tell from these slides, from the control group, which has no supplement of the build rate, the salmonella burden is quite high than those groups of birds which has been treated with build rate. So they follow up to see, what's the reason for it. They investigate the mechanisms. So they did in vitro studies with KK2, I believe KK2 cells, and they look at the salmonella pathogenicity island 1, and this island 1 basically contains most genes which are responsible for gut invasion. They found here A, these particular genes are significantly downregulated, even though most other genes were also downregulated. And they follow up with the mutation. They make the mutant of the KOA, and to see if they can see the similar results in the in vivo studies. By doing this, as you can see from the right side of panels, the wild type actually, now salmonella shedding is pretty higher than the mutant which has been indicated down is much lower salmonella shedding compared to the wild type. So this basically approved that HLA is signal, and the build rate can suppress the signal, therefore to achieve the result to reduce the salmonella burden and the infection. And they also, they flip the coin around, say, okay, if we have some bacteria, build rate producing bacteria, so what's the story? And as you can see from this slide, so you can see on day 40, so I'm not going to go to all the data, I just specifically point out day 40, you look those, they divide into male and the female, but they also have all the birds. You look those feet conversion ratio. And the butyrin-producing bacteria treated the group had much better feeding efficiency compared to the control group, which received no butyrin-producing bacteria. They also looked into the microbiota, and on day 25 or day 26, that's the top panel here. I didn't see, okay, top panel here. So they found the two major differences. One, I believe, is the one is the bacteroids, and the other one is the butyrin-produced bacteria. So you can they found like the butyrin supplement and the chicken supplement with the butyrin-produced bacteria had significant bacteroids population. Yeah, and also on day 40, they also found the difference and the lactobacillus group, and also the birds received butyrin-producing bacteria also have a high abundance of lactobacillus in the guts. In addition, they also look at the supplement of the butyrin-producing bacteria on the challenge in the birds is NE disease. They have done 4 consecutive trials with the birds were challenging with Clostridium perfringens. And for those control group which had no supplement of the butyrin-producing bacteria, had significantly high NE lesions and also the instance of the NE disease compared to the group which had received the butyrin-producing bacteria. So all the whole story, I think it's pretty good. So basically, it indicates the butyrin can specifically suppress some enteric pathogens, and also because they can also by suppress some specific genes, their expression. And the next few slides, so I want to talk our own work. It's also, this is the actual build rate. We have seen one phenomenon when we do the chicken trials. When the birds get into the week 3, and we found the birds receiving the build rate had significant reduction of the abdominal fat deposition. So this is what you can tell from the show in the left panel. We tested 2 different chicken strains. One's RAS 308, one's 708. The open panel, open bars are the control group birds which receive no build rate. And those colored one's supplement with 500 ppm, the other one supplement with 2,000 ppm butyrin. So regardless the supplementation or not, the 708 has much less, has significantly reduced the abdominal fat deposition compared to RAS 308. And also, supplementation of the butyrin can further reduce the abdominal fat deposition in the birds. We also look into if the supplementation butyrin can enhance the breast muscle. As previous reports described, there's positive effect. In our hand, we also confirm this. Supplementation of the butyrin can enhance the breast muscle production, as indicated by the right panel. So, what's the mechanism behind this? So we carried out the further studies. First, we examine the host response. We look at those key enzymes in lipid metabolism. So This slide lists like 4 major key factors. One is carbon carboxylase and fatty acid synthesis, and also lipoprotein lipase, and the total serum cholesterol. And we found all these enzymes key factors were downregulated, was decreased by the supplementary, by the treatment of the build rate. And we did the RNA-seq analysis, and we found out one of the major signal pathways as a PR, which respond for the lipid metabolism, some of enzymes, some of key points were downregulated, as indicated by those squares. The with dot lines outside, that's downregulated, with a solid outside is upregulated. So in the conclusion from this, put together would be the effect of the build rate on the lipid metabolism would be downregulate lipid synthesis and the lipid storage and lipid transportation and secretion. Interestingly, the oxidation of lipids and the fatty acid also increased. So this put together is a nice story and fit in what are observed. The first question we ask, if microbiota contribute to this phenomena, we did the 16S RNA sequence to look at the community structure and the composition. We also analyzed the serum metabolites with the NMR techniques. And on the left hand, you can see the beta diversity of the microbiota. So you can clearly cluster, separate each other. So that means there is a treatment effect. Basically, treatment of bilirubin has an effect on the microbiota and compositions. We also identify 30, I think more than 30 key bacteria, key composition of microbiota, and as indicated by the top of the heat map panels. And also we follow up with a real-time PCR analysis. We identified that among those bilirubin-producing bacteria, like a class 14, class 4, we didn't see any changes in their abundance in the population. However, we identified both abundance and the species diversity of bilirubin significantly increased by the treatment of the build rate. And look at this in the results shows the results of the serum analysis, and those items in red are the metabolites is bacterial metabolites. So you can see all we examined metabolites upregulated. So, and also we use the principal component analysis, and also shows the cluster, the treatment effect separate from those on treatment. So as a conclusion for these studies, and also we look at a lot of literatures. The one science paper that mentioned, like say, build rate and Campylobacter can modulate lipid metabolism and glucose homeostasis. This actually fit in our observations, and therefore we propose that this bifidobacteria can contribute to the decrease of the abdominal fat deposition in the chickens. So that's the story we got from our studies. So the take-home message would be the build rate can benefit gut digestive and absorptive functions. It can enhance gut integrity. It can reduce the inflammation and the enteric infections, and also improve the gut microbiota, finally, to achieve the goal to promote animal growth performance. But one thing I also want to point out, as the previous speaker said, everything is dynamic and balanced. So everything has its limits. So whenever you make a conclusions, then you need to look under what conditions. Yeah, that need to keep kept in mind. That's all my talk today. Thank you for your attention.